Tonight, we're going to explore something that will completely change how you understand our place in the universe. We're going to discover the true scale of the Andromeda Galaxy. Not just the numbers you might have heard before, but what those numbers actually mean. By the end of this journey, you're going to understand a structure so vast that it challenges the limits of human comprehension. Before we start, if you enjoy these deep explorations of space, a quick like or subscribe would really help the channel grow. Now, let's begin our journey to the nearest large galaxy beyond our own. Let's start with something you can actually do tonight. Finding Andromeda with your own eyes. On a dark night, far from city lights, you can see this galaxy without any equipment. It appears as a fuzzy oval patch in the constellation Andromeda, which shares the galaxy's name. The constellation itself comes from Greek mythology, named after an Ethiopian princess. To find it, first locate Cassiopeia, the W-shaped constellation. From the center of the W, trace a line toward the constellation Pegasus. About halfway along that path, you'll find the fuzzy patch. That's Andromeda. To the naked eye, on a truly dark night, Andromeda appears as an elongated fuzzy patch, roughly the size of 2 or 3 full moons placed end to end, about 1.5 to 2 degrees long. But that's just the bright central region. In long exposure photographs, especially those that include ultraviolet and hydrogen alpha light, the galaxy stretches dramatically farther. The full disk now measures roughly 5 to 6 degrees across, 10 to 12 full moons side by side, making it the largest deep sky object visible without a telescope. The commonly quoted figure of 30 full moons came from older misunderstandings, but the real photographic extent is still far larger than what your eyes can detect. Ancient observers noticed this fuzzy patch over 1,000 years ago. The Persian astronomer Abd al-Rahman al-Sufi described it in the year 964, calling it a small cloud. He had no idea what he was looking at. Chinese astronomers also recorded it centuries earlier. For a long time, astronomers assumed it was a nebula, a cloud of gas somewhere within our own stellar system. The truth turned out to be far more extraordinary. In the 1920s, Edwin Hubble used the 100-inch telescope at Mount Wilson to resolve individual stars within the fuzzy patch. By measuring certain variable stars called Cepheids, he calculated the distance and proved something revolutionary. This wasn't a nearby cloud, it was an entire galaxy of stars far beyond the boundaries of the Milky Way. Andromeda sits 2.54 million light-years from Earth. Let's break down what that actually means. Light travels at about 300,000 kilometers per second, or 186,000 miles per second. Nothing in the universe moves faster. In 1 year, light covers roughly 9.5 trillion kilometers, or 5.9 trillion miles. We call this distance a light year. Now, multiply that by 2.54 million. The distance to Andromeda is approximately 24 quintillion kilometers. That's 24 with 18 zeros after it, or about 15 quintillion miles. Here's some perspective on that distance. Sunlight takes 8 minutes and 20 seconds to reach Earth. If the sun suddenly vanished, we wouldn't know for over 8 minutes, because the light telling us it's gone would still be traveling toward us. Light from Proxima Centauri, the nearest star beyond our sun, takes 4.24 years to arrive. But light from Andromeda takes 2.5 million years. The light entering your eyes when you look at Andromeda tonight left that galaxy when early humans on Earth were just beginning to use stone tools. Homo habilis walked the African savannas. No modern humans existed yet. The entire span of recorded human history, all of civilization, represents less than 1/4 of the time that light has been traveling from Andromeda to reach us. If you could somehow board a spacecraft and travel at light speed, the fastest speed physics allows, you still wouldn't reach Andromeda until 2.5 million years had passed. The fastest spacecraft humans have actually built, the Parker Solar Probe, reaches speeds of about 700,000 kilometers per hour, or 430,000 miles per hour, at its closest approach to the Sun. At that speed, reaching Andromeda would take roughly 3.9 billion years. That's nearly as long as Earth has existed. The Voyager 1 spacecraft, launched in 1977 and now humanity's most distant object, travels at about 61,000 kilometers per hour or 38,000 miles per hour. At Voyager's speed, the journey would take over 44 billion years. That's more than 3 times the current age of the universe. Andromeda is a barred spiral galaxy. This means it has a bar-shaped concentration of stars at its center, with spiral arms extending from the ends of that bar. Our Milky Way shares this basic structure. The galaxy measures approximately 220,000 light-years in diameter. To cross from one edge to the other, even at light speed, would take longer than modern humans have existed on Earth. The Milky Way, by comparison, spans about 100,000 light-years. Andromeda is substantially larger, roughly 1.5 times the Milky Way's diameter on the latest estimates. The galaxy contains roughly 1 trillion stars. Each one is a sun, potentially with its own retinue of planets, moons, and smaller bodies. Our Milky Way contains somewhere between 100 billion and 400 billion stars. Andromeda has roughly 2 to 3 times our number. If you started counting stars in Andromeda at a rate of 1 per second, never stopping to eat, sleep, or rest, you would need approximately 32,000 years to finish. That's longer than the entire span of human civilization, from the first cities to today. The total mass of Andromeda, including all its stars, gas, dust, and dark matter, comes to approximately 1.5 to 2 trillion times the mass of our Sun. At the center of this immense structure sits a supermassive black hole with a mass of roughly 140 million times our Sun. For comparison, the black hole at the Milky Way's center, Sagittarius A star, has a mass of only about 4 million solar masses. Andromeda's central black hole is roughly 35 times more massive. For years, astronomers debated whether Andromeda might actually have 2 supermassive black holes at its core, based on a double nuclear structure visible in images. This was a popular theory in the early 2000s. However, more recent observations and analysis, particularly from 2020 onward, have largely ruled this out. The current scientific consensus points to a single black hole surrounded by an eccentric disk of stars. The double structure we see results from the way stars orbit the central black hole in an off-center, elongated disk. It's a fascinating optical effect, but not evidence of a binary black hole system. The central bulge of Andromeda is enormous. It spans roughly 30,000 light-years across. That's almost 1/3 the entire diameter of the Milky Way. This bulge contains several hundred billion-old stars packed into a relatively small volume. The stellar density here is thousands of times higher than in our solar neighborhood. If you lived on a planet near Andromeda's core, assuming you could survive the intense radiation environment, your night sky would be transformed. Thousands of stars would shine brightly enough to cast shadows. The combined starlight would create a perpetual twilight, making true darkness impossible. These core stars are predominantly population 2 stars, the older generation born when the galaxy was young. They're metal poor in astronomical terms, meaning they contain relatively few elements heavier than hydrogen and helium. These stars formed from primordial gas that hadn't yet been enriched by previous generations of stellar death. They glow with a reddish hue, characteristic of older, cooler stars. Red giants dominate the central bulge, stars that have exhausted their core hydrogen and swollen to enormous sizes. Some of these red giants are larger than Earth's entire orbit around the Sun. The extreme stellar density near the core creates unique astrophysical environments. Stars pass close enough to each other that gravitational interactions become common. Binary star systems can be disrupted, with one star captured by a new partner, while the other is flung away at high speed. Occasionally, stars venture too close to the central black hole. The black hole's immense tidal forces stretch the star into a long stream of gas, an event astronomers call a tidal disruption event. The gas spirals into the black hole, heating to millions of degrees and emitting intense X-rays before disappearing forever beyond the event horizon. The black hole itself isn't particularly active right now. It's not consuming large amounts of matter, but this quiescent state could change. If a large gas cloud or an entire star were to wander too close, the black hole would devour it violently. The infalling material would form an accretion disk, a swirling maelstrom of superheated gas. The disk would emit more light than the rest of the galaxy combined. Jets of particles might shoot outward perpendicular to the disk at nearly the speed of light, creating a quasar, or active galactic nucleus. Andromeda would transform from a peaceful spiral into one of the most energetic objects in the local universe. Moving outward from the bulge, we encounter the spiral arms. These aren't rigid structures like the arms of a pinwheel. They're density waves, regions where stars and gas temporarily bunch up as they orbit the galactic center. Think of traffic on a circular highway. Cars move at relatively constant speed, but traffic jams form and dissolve as cars bunch together, then spread out. The jam moves around the highway at a different speed than the individual cars. Spiral arms work similarly. They're waves of compression moving through the galactic disk, and stars pass through them during their orbits. The spiral arms appear bright because they're where most star formation occurs. When the density wave passes through a region, it compresses the gas clouds. This compression can trigger gravitational collapse, causing the clouds to fragment and form new stars. The most massive stars born in these events shine brilliantly in blue light. These O and B type stars are spectacularly luminous, each one outshining the sun by factors of thousands or even millions. But they burn through their nuclear fuel quickly, living only a few million years before exploding as supernovae. They barely have time to move away from their birthplaces before dying, which is why they remain concentrated in the spiral arms. Andromeda's spiral structure isn't perfectly symmetrical. One side appears more prominent than the other. This lopsidedness likely results from gravitational interactions with other galaxies. About 800 million years ago, Andromeda experienced a major merger with another large galaxy. The collision disrupted the orderly spiral pattern, creating asymmetries that persist to this day. Computer simulations of galaxy mergers show that it takes billions of years for the disturbed structure to fully relax back into symmetry. Andromeda is still recovering from this ancient collision. Within the spiral arms lie enormous molecular clouds, the coldest and densest regions of interstellar space. These clouds can span hundreds of light years and contain enough material to build millions of stars. The gas is primarily molecular hydrogen, along with carbon monoxide, ammonia, and more complex organic molecules. Dust grains mixed with the gas provide surfaces where molecules can form. The clouds are opaque to visible light, appearing as dark silhouettes against the background stars. But infrared telescopes can penetrate the dust, revealing the warm protostars forming inside. Star formation in Andromeda isn't evenly distributed. There's a prominent ring of enhanced star formation about 32,000 light-years from the center. This ring lights up dramatically in ultraviolet images, showing concentrations of young, hot stars. The ring's origin isn't completely understood, but it likely relates to the central bar structure. Bars can channel gas inward or outward, creating resonances at specific radii where gas accumulates and star formation intensifies. This ring contains thousands of stellar nurseries, each one a cauldron where new suns are being born. The disk of Andromeda is where most of the galaxy's stars reside. Unlike the spherical bulge and halo, the disk is remarkably flat. It's about 1,000 light-years thick at the Sun's location in the Milky Way, and Andromeda's disk has similar proportions. This flattening results from rotation. As the galaxy formed, the gas and stars that would become the disk settled into a plane perpendicular to the rotation axis, just as pizza dough flattens when spun. The disk rotates, but not like a solid wheel. Different parts rotate at different speeds. Near the center, stars complete their orbits in a few tens of millions of years. Farther out, orbital periods stretch to hundreds of millions of years. In the outermost regions, a single orbit takes over 1 billion years. This differential rotation should wind the spiral arms tighter over time, like stirring honey. Yet the arms persist. That's because they're density waves, not material structures. The wave pattern can maintain itself even as individual stars and gas clouds move through it. By measuring the rotation speeds at different distances from the center, astronomers can map out the galaxy's mass distribution. This is where dark matter makes its presence known. The visible matter, all the stars and gas, can't account for the rotation speeds observed in the outer regions. Stars are moving faster than they should based on the gravity from visible matter alone. Either our understanding of gravity is wrong, which seems unlikely given how well it works everywhere else, or there's additional mass we can't see. That invisible mass is dark matter, and it dominates Andromeda's mass budget. The disk also contains older stars mixed with the young ones. These are population 1 stars like our Sun, formed more recently from gas enriched with heavy elements. They've had time to drift away from the spiral arms where they were born. Some follow nearly circular orbits in the plane of the disk. Others travel on elliptical paths that carry them above and below the plane. The Sun, for example, oscillates up and down through the Milky Way's disk as it orbits the center. Stars in Andromeda follow similar patterns. How do we actually know Andromeda is 2.54 million light-years away? This question takes us into one of astronomy's most fundamental challenges, measuring distances across space. You can't simply point a radar gun at Andromeda. The distances are too vast for direct measurement. Instead, astronomers use what's called the cosmic distance ladder, a series of methods that build on each other, each reaching farther into space. The foundation of the distance ladder starts right here in our solar system. We can measure distances to nearby objects like the Moon using radar, send a radio pulse, time how long it takes to bounce back, and calculate the distance. For more distant solar system objects, we use geometry. As Earth orbits the Sun, nearby objects appear to shift position against the background stars. This shift, called parallax, lets us calculate distances using simple trigonometry. These methods give us the baseline, the astronomical unit, Earth's distance from the Sun at about 150 million kilometers or 93 million miles. For nearby stars, parallax still works. The Hipparcos satellite and later the Gaia spacecraft have measured parallaxes for billions of stars in our galaxy. But parallax only works out to a few thousand light-years. Beyond that, the shifts become too small to measure accurately. For greater distances, we need a different technique. That's where standard candles come in. A standard candle is an object whose true brightness we know. By measuring how bright it appears from Earth, we can calculate how far away it must be. It's like seeing a light bulb and knowing it's a 100-watt bulb, figuring out how far away it is based on how dim it looks. The most important standard candle for measuring distances to nearby galaxies is a type of variable star called a Cepheid. Cepheids are massive stars that pulsate, growing brighter and dimmer in a regular cycle. The key discovery, made by Henrietta Swan-Leavitt in 1912, is that a Cepheid's pulsation period is directly related to its true luminosity. Measure the period, and you know how bright the star really is. Compare that to how bright it appears, and you can calculate the distance. It's an elegant method that revolutionized astronomy. Edwin Hubble used this technique in the 1920s to measure the distance to Andromeda. He identified Cepheid variables in the galaxy using the 100-inch telescope at Mount Wilson Observatory. By measuring their periods and apparent brightnesses, he calculated that Andromeda was roughly 900,000 light-years away. This was an underestimate, because he didn't know there are actually two types of Cepheids with different period luminosity relationships. But it was close enough to prove Andromeda was far beyond the Milky Way. Modern measurements, using the Hubble Space Telescope, an improved understanding of Cepheids, have refined the distance to 2.54 million light-years with an uncertainty of only a few percent. For galaxies too distant to resolve individual Cepheids, astronomers use even brighter standard candles. Type Ia supernovae, exploding white dwarf stars, are so luminous they can be seen billions of light-years away. These explosions have remarkably consistent peak brightnesses, making them excellent distance indicators. By calibrating the Type Ia supernova scale using galaxies where we know the distance from Cepheids, we can measure distances across cosmological scales. This technique helped discover that the universe's expansion is accelerating, a discovery that won the Nobel Prize in 2011. The cosmic distance ladder is like climbing a mountain. Each rung takes you higher, but you need the lower rungs to be solid or everything above becomes uncertain. Andromeda sits on a crucial rung. It's close enough to measure accurately using Cepheids, yet far enough to serve as a calibration for more distant measurements. Understanding Andromeda's distance helps us understand the entire scale of the universe. Let's explore the lives of stars within Andromeda, because understanding stellar evolution helps us understand the galaxy itself. Stars aren't static objects. They're born, they live for millions or billions of years, and they die. Each phase contributes differently to the galaxy's appearance and evolution. Stars form in molecular clouds when gravity overcomes the pressure from gas and turbulence. A cloud fragment collapses, heating as it shrinks. When the core temperature reaches about 10 million degrees, hydrogen fusion ignites. The star has been born. What happens next depends entirely on the star's mass. Mass is destiny in stellar evolution. A star's mass at birth determines its luminosity, temperature, lifetime, and ultimate fate. The smallest stars, red dwarfs with less than 40% the sun's mass, burn hydrogen slowly and efficiently. They can live for trillions of years, far longer than the current age of the universe. Every red dwarf that has ever formed is still shining today. These stars dominate the stellar population numerically. In Andromeda, as in all galaxies, red dwarfs are the most common stars. But they're faint, contributing little to the galaxy's overall light. You need large telescopes to see individual red dwarfs, even in nearby galaxies. Medium-mass stars like our Sun live for billions of years. The Sun has been shining for about 4.6 billion years. and will continue for roughly another 5 billion. During its main sequence lifetime, it fuses hydrogen in its core at a steady rate. Eventually, the core hydrogen will be exhausted. The core will contract and heat while the outer layers expand. Our star will become a red giant, swelling to roughly the orbit of Earth or Mars. After a few 100 million years as a red giant, the Sun will shed its outer layers in a planetary nebula, leaving behind a white dwarf core. That white dwarf will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark cinder. Massive stars, those born with more than 8 times the Sun's mass, live fast and die young. They burn through their fuel at prodigious rates. A star 20 times our star's mass might live only 10 million years. These stars shine brilliantly, pumping out more light than 1 million suns. They dominate the ultraviolet output of galaxies and ionize vast nebulae around them. When they exhaust their core fuel, they don't go gentle. They explode as supernovae, outshining entire galaxies for a few weeks. The core collapses, forming either a neutron star or, if massive enough, a black hole. The explosion ejects the outer layers at speeds of tens of thousands of kilometers per second, blasting enriched material back into the interstellar medium. In Andromeda right now, all these stages are occurring simultaneously. Red dwarfs are being born and will shine for eons. Medium mass stars are on the main sequence, steadily fusing hydrogen. Red giants are swelling and cooling. Planetary nebulae are expanding, their central white dwarfs exposed and fading. And somewhere, perhaps several times per century, massive stars are exploding as supernovae. Each supernova releases as much energy in a few weeks as the Sun will emit over its entire 10 billion year lifetime. The energy input from supernovae drives galactic winds, heats the interstellar medium, and can trigger new star formation in nearby clouds. The chemical composition of Andromeda has changed over time due to stellar evolution. The earliest stars formed from pristine gas, mostly hydrogen, and helium left over from the Big Bang. When those stars died, they returned material enriched with carbon, oxygen, neon, and heavier elements forged in their cores. Subsequent generations formed from increasingly enriched gas. Today's stars contain about 2% heavy elements by mass, enough to form rocky planets. This chemical evolution is crucial. Without it, planets like Earth couldn't exist, and neither could life. Binary stars add another layer of complexity. About half of all stars form in binary or multiple star systems. In close binaries, the stars can interact, transferring mass from one to the other. If one star evolves into a white dwarf, while the other is still on the main sequence, the white dwarf can accrete material from its companion. If enough material accumulates, the white dwarf's core can ignite in a runaway thermonuclear explosion, a type Ia supernova. These are the standard candles used for cosmological distance measurements. Andromeda produces roughly one type Ia supernova every few hundred years on average. Andromeda isn't just stars and gas. It's also permeated by magnetic fields and cosmic rays, high-energy particles racing through space at nearly the speed of light. These components are invisible to optical telescopes, but play crucial roles in galactic dynamics. Magnetic fields in galaxies are generated through a process called the dynamo effect. Moving electrically conducting fluids, in this case ionized gas orbiting the galaxy, can generate and amplify magnetic fields. Over time, the galaxy's rotation twists and stretches the field lines, building up field strength. The resulting magnetic field follows the spiral arms. With field strengths typically around 10 microgauss, about 100,000 times weaker than Earth's magnetic field. That might sound weak, But across galactic scales, these fields have significant effects. Magnetic fields provide pressure support, helping to hold up gas clouds against gravity. They also affect the motion of charged particles. Cosmic rays, which are mostly protons and atomic nuclei, accelerated to tremendous energies, spiral along magnetic field lines. The fields confine cosmic rays within the galaxy, preventing them from escaping immediately into intergalactic space. This confinement is important because cosmic rays contribute energy and pressure to the interstellar medium. Where do cosmic rays come from? The primary source is supernova remnants. When a massive star explodes, the expanding shock wave can accelerate particles to relativistic speeds through a process called diffusive shock acceleration. These particles become cosmic rays. Some reach energies millions of times higher than anything we can produce in particle accelerators on Earth. When cosmic rays collide with gas in the interstellar medium, they produce gamma rays and other secondary particles. By detecting these gamma rays with satellites, astronomers can map out where cosmic rays are concentrated in Andromeda. Radio telescopes also detect emission from cosmic rays. As the particles spiral through magnetic fields, they emit synchrotron radiation at radio wavelengths. The radio brightness of a galaxy correlates with its star formation rate because more supernovae means more cosmic ray acceleration. Andromeda is a strong radio source, though not as strong as some actively star-forming galaxies. The radio emission traces the spiral arms and shows where magnetic fields are strongest. Magnetic fields also affect star formation. When a molecular cloud begins to collapse, magnetic fields can provide support against gravity, slowing the collapse. For star formation to proceed, the field must somehow be weakened or removed from the core of the cloud. This might happen through a process called ambipolar diffusion, where neutral gas gradually drifts through the ionized gas that's coupled to the magnetic field. Understanding this process is crucial for understanding why stars form at the rates they do. In the halo of Andromeda, magnetic fields are weaker and more tangled. They might be generated by outflows from the disk, material blown outward by supernovae and stellar winds. Or they might be remnants from the galaxy's formation, stretched and twisted over billions of years. Observing these faint halo fields is challenging, requiring sensitive radio observations. But they tell us about the galaxy's history and about how energy and material are transported between the disk and the surrounding environment. Scattered throughout Andromeda are thousands of nebulae, clouds of glowing gas illuminated by nearby stars. These nebulae come in several varieties, each telling a different story. The most common are H2 regions, also called emission nebulae. These are clouds of hydrogen gas ionized by ultraviolet radiation from hot young stars. When ultraviolet photons strike hydrogen atoms, they knock off the electrons, ionizing the gas. Eventually, the electrons recombine with protons, emitting light at specific wavelengths. The strongest emission line is H-alpha, at 663 nanometers, which gives emission nebulae their characteristic reddish color in photographs. Andromeda contains thousands of H2 regions, ranging in size from a few light-years to over 1,000 light-years across. The largest are comparable to the Tarantula Nebula in the Large Magellanic Cloud, itself one of the most massive star-forming regions in the local group. These giant H2 regions contain enough ionized gas to make thousands of stars. They're powered by clusters of O and B stars, the hottest and most luminous stars that form from massive molecular clouds. A single O star can ionize a region hundreds of light-years across. When dozens of O stars form together, as they often do, the result is a spectacular emission nebula visible across millions of light-years. Planetary nebulae are a different type of emission nebula. Despite the name, they have nothing to do with planets. The term comes from early observers who thought they looked like planetary disks through small telescopes. Planetary nebulae are the ejected outer layers of dying medium-mass stars. When a star like the Sun exhausts its core fuel and becomes a red giant, instabilities develop. The star pulsates, throwing off shells of gas. Eventually, the hot core is exposed, a young white dwarf with a surface temperature exceeding 100,000 degrees. Ultraviolet radiation from this core ionizes the surrounding gas shells, making them glow. Andromeda hosts thousands of planetary nebulae. Each one is the death announcement of a star, visible for a few tens of thousands of years before the gas disperses and becomes too faint to see. By cataloging planetary nebulae, astronomers can estimate how many medium-mass stars have died in Andromeda over the past few billion years. The shapes of planetary nebulae are often complex and beautiful, with rings, jets, and multiple shells. These structures result from the complex interplay of stellar winds, magnetic fields, and binary interactions. Many, perhaps most, planetary nebulae result from binary star systems where the companion's gravity shapes the ejected material. Supernova remnants represent the violent deaths of massive stars. When a supernova explodes, it blasts its outer layers into space at speeds of tens of thousands of kilometers per second. This material crashes into the surrounding interstellar medium, creating a shock wave. The shock heats the gas to millions of degrees, causing it to emit X-rays. The remnant expands over thousands of years, gradually slowing and cooling. Eventually, after a few 100,000 years, the remnant fades and merges with the general interstellar medium, but not before injecting enormous amounts of energy and enriched material into the galaxy. Andromeda produces supernovae at a rate of roughly 2 to 3 per century, combining both core collapse supernovae from massive stars and type Ia supernovae from exploding white dwarfs. Each leaves behind a remnant. Astronomers have identified dozens of supernova remnants in Andromeda using X-ray observations. The youngest and brightest are still visible in optical light as well, glowing with the energy from the explosion. Studying these remnants tells us about the explosion mechanisms, the progenitor stars, and how supernovae affect their surroundings. Reflection nebulae are clouds of dust that reflect the light of nearby stars. Unlike emission nebulae, where gas is ionized and glows on its own, reflection nebulae simply scatter starlight. They appear blue in photographs because blue light scatters more efficiently than red light, the same reason Earth's sky is blue. Reflection nebulae are typically found near young star clusters, where dust hasn't yet been cleared away. They're common in star-forming regions, often associated with the molecular clouds from which the stars formed. Dark nebulae are molecular clouds so dense and dusty that they block background starlight completely. They appear as dark patches against the brighter background of stars or emission nebulae. The most famous example in our sky is the Coalsack Nebula, but Andromeda contains thousands of such clouds. These are the sites of future star formation. Inside these dark nebulae, gravity is slowly gathering material, preparing the next generation of stars. The visible disk of Andromeda, bright and full of stars, doesn't represent the galaxy's true extent. Beyond the main disk lies an extended envelope of stars and gas reaching far into intergalactic space. This outer region is faint and difficult to detect, but it's real and substantial. The stellar halo extends to at least 500,000 light-years from the center, more than twice the radius of the visible disk. This halo contains about 1% of the galaxy's stars, but spread over such a large volume that the density is incredibly low. If the Sun were in Andromeda's outer halo, The nearest star might be hundreds of light-years away instead of the 4.2 light-years to Proxima Centauri. The night sky would be spectacularly dark, with the bright core of Andromeda dominating one part of the sky, but otherwise very few stars visible. The stars in the outer halo are almost entirely old population, 2 stars and the remnants of disrupted satellite galaxies. When a dwarf galaxy falls into Andromeda and gets torn apart by tidal forces, its stars get scattered along its former orbit, creating a stream. Over time, these streams spread out and phase mix, gradually losing their identity and merging into the general halo population. But the process takes billions of years. So at any given time, the halo is full of substructure, streams, shells, and overdensities marking recent and ongoing mergers. Deep imaging surveys have mapped this substructure in exquisite detail. The Pan-Andromeda Archaeological Survey, or PANDAS, used the Canada-France-Hawaii telescope to image an enormous area around Andromeda, revealing dozens of stellar streams and shells. Each one tells a story of a smaller galaxy that came too close and paid the ultimate price. By mapping these features, astronomers can reconstruct Andromeda's merger history over the past few billion years. The picture that emerges is one of ongoing growth through cannibalism. Andromeda has consumed dozens of smaller galaxies and continues to do so today. The gas also extends beyond the visible disk. Neutral hydrogen has been detected out to enormous distances using radio telescopes. The HI disk is warped, with one side extending farther than the other and the outer regions tilted relative to the inner disk. This warping is common in galaxies and often results from interactions with other galaxies, or from the accretion of gas from intergalactic space falling in along preferred directions. Andromeda's warp might be related to its past merger history or to ongoing interactions with its satellite galaxies. There's also a vast reservoir of hot, ionized gas in the halo. This gas has been detected through its absorption of light from background quasars and through X-ray emission. The gas is heated to hundreds of thousands or millions of degrees by supernova explosions in the disk and by accretion of material falling into the galaxy. This hot halo contains a substantial fraction of the galaxy's baryonic matter, possibly as much mass as all the stars and cold gas combined. It's part of the galaxy's ecosystem, material that has been ejected from the disk by energetic processes and will eventually cool and fall back in to form new stars. Understanding the outer regions of Andromeda is crucial for understanding how galaxies acquire their mass. Galaxies don't form in isolation. They're embedded in dark matter halos and surrounded by the cosmic web, filaments of gas connecting galaxies across vast distances. Material flows along these filaments, feeding into galaxies over time. Andromeda is still accreting material from its surroundings, gradually growing more massive. This accretion will continue for billions of years, though the rate is slowing as the universe expands and nearby gas reservoirs are depleted. Galaxies evolve slowly by human standards. Andromeda looks essentially the same today as it did when our ancestors were painting caves 40,000 years ago. It will look essentially the same 40,000 years from now. The changes happen on timescales of millions or billions of years, far too slow for individual humans to perceive. But the changes are real and profound. Consider star formation. Andromeda currently forms about 1 solar mass worth of new stars each year. That might sound like a lot, but spread across the entire galaxy, it's actually quite modest. In 1 million years, the galaxy will have formed 1 million new stars, mostly small red dwarfs with a few massive stars mixed in. That's barely noticeable against the backdrop of 1 trillion existing stars. But over 1 billion years, It adds up to 1 billion new stars, enough to make a measurable difference in the galaxy's overall luminosity and mass. At the same time, stars are dying. Every year, hundreds of stars in Andromeda complete their lives. Most are medium or low-mass stars, becoming white dwarfs. A few massive stars explode as supernovae. These deaths return material to the interstellar medium, enriching it with heavy elements. The balance between star formation and stellar death determines how the galaxy's stellar population evolves over time. Currently, Andromeda is forming fewer new stars than it's losing to death, meaning the average age of stars in the galaxy is slowly increasing. Andromeda is gradually aging, transitioning toward a more mature, quiescent state. The merger with satellite galaxies also changes the structure slowly. Each time a dwarf galaxy is disrupted, its stars join Andromeda's halo. Over time, this builds up the halo population and adds slight amounts of mass to the galaxy. The process is ongoing. M32 and M110 are being torn apart right now. In a few billion years, they'll be completely absorbed. Other satellites will follow. This slow accumulation of smaller systems is how large galaxies like Andromeda grow. The approach toward the Milky Way is another slow change. The two galaxies are closing at about 110 kilometers per second. That's fast by human standards, but across 2.5 million light-years, it translates to a closing time of billions of years. Each million years, the gap shrinks by roughly 100 light-years. It's like watching paint dry on a cosmic scale. You can't see it happening, but it's inexorable. Even the orbits of stars within the galaxy change slowly. A star on an elliptical orbit gradually precesses, meaning the orientation of its orbit slowly rotates over time. Close encounters with other stars or massive gas clouds can perturb orbits, nudging stars onto slightly different paths. Over hundreds of millions or billions of years, these tiny perturbations add up. The orbital structure of the galaxy slowly evolves, though not enough to fundamentally change the overall appearance. The longest timescale is the evolution of the dark matter halo. Dark matter particles orbit within the halo, but they don't interact except through gravity. The halo's shape and density profile evolve very slowly as the galaxy accretes new material from its surroundings and as mergers bring in additional dark matter. Computer simulations show that dark matter halos can remain stable for many billions of years, changing only gradually unless disrupted by major mergers. All these processes together drive galactic evolution. Andromeda is not static. It's a dynamic system, constantly changing on timescales far longer than human lifetimes, but short compared to cosmic time. Understanding these changes helps us understand how all galaxies evolve and how the universe itself changes over time. We've mentioned observing Andromeda across the electromagnetic spectrum, but let's dive deeper into what each wavelength reveals. Different types of radiation come from different physical processes and probe different aspects of the galaxy. Radio waves, the longest wavelength radiation, reveal several phenomena. The 21-centimeter line of neutral hydrogen maps the distribution of cold atomic gas. This is the most abundant form of matter in the outer disk and halo. Radio continuum emission, produced by synchrotron radiation from cosmic rays spiraling through magnetic fields, traces high-energy particles and magnetic field structure. And molecular emission lines, particularly from carbon monoxide, reveal the coldest, densest gas where stars form. Radio observations are invaluable because radio waves pass through dust that blocks visible light, allowing us to see into regions hidden from optical telescopes. Microwaves bridge the gap between radio and infrared. thermal emission from cold dust produces microwaves. This dust has temperatures of only 10 to 30 degrees above absolute zero, too cold to emit visible or even infrared light, but warm enough to glow in microwaves. Observations at these wavelengths map the coldest dust and the molecular clouds embedded within it. The Planck satellite has observed Andromeda at microwave wavelengths, revealing the large-scale structure of cold dust throughout the galaxy. Infrared observations reveal warm dust and cool stars. Dust heated by nearby stars to temperatures of a few tens to a few hundred degrees emits strongly in the infrared. These warm dust regions mark sites of recent or ongoing star formation because young stars heat their surroundings. Mid-infrared observations from the Spitzer Space Telescope beautifully mapped Andromeda's spiral arms, showing them as bright lanes filled with warm dust and star-forming regions. Infrared also reveals cool red giant stars that emit most of their light at these wavelengths. Visible light is what our eyes see. This is the radiation from stars themselves, primarily from their photospheres, the visible surfaces. Blue and ultraviolet light comes from hot young stars. Yellow light comes from medium temperature stars like the Sun. Red light comes from cool stars and red giants. By observing in different colors, astronomers can determine stellar temperatures and distinguish between young and old stellar populations. The spiral arms appear bright in blue light due to young stars, while the bulge appears yellow-red from old stars. Ultraviolet radiation comes from the hottest stars, those with surface temperatures above 10,000 degrees. The most massive O and B stars emit most of their light in ultraviolet wavelength. Ultraviolet observations highlight regions of recent star formation and ionize the surrounding gas, creating H2 regions. The Galaxy Evolution Explorer mapped Andromeda in ultraviolet, revealing the intricate structure of the spiral arms and identifying thousands of star-forming regions and hot star clusters. The most violent places in the universe reveal themselves at the highest energies. Gas, heated to millions of degrees, glows brightly in X-rays. Supernova remnants radiate intensely as their shock waves slam interstellar material to extreme temperatures. In close binary systems, matter falling onto a neutron star or black hole converts gravitational energy into tremendous heat right before it disappears, producing powerful X-ray emission. Even the supermassive black hole at a galaxy's heart can flare when it feeds. Thanks to Chandra, Andromeda, our calm-looking neighbor is mapped in exquisite detail, exposing hundreds of blazing binaries, remnants, and other high-energy objects hidden in plain sight. Gamma rays, the highest energy radiation, come from the most extreme processes. Cosmic ray collisions with interstellar gas produce gamma rays through particle interactions. Pulsars, rapidly spinning neutron stars, can emit beams of gamma rays, and certain types of supernovae produce radioactive isotopes that decay and emit gamma rays. Detecting gamma rays from Andromeda is challenging because they're rare and hard to focus. But space-based gamma-ray telescopes like Fermi have detected the galaxy, showing that high-energy processes are active there. By combining observations from all these wavelengths, astronomers build comprehensive pictures of galaxies. No single wavelength tells the whole story. Visible light shows stars, but misses hidden star formation. Radio reveals gas, but doesn't directly show stars. X-rays highlight energetic events, but miss the normal stars that make up most of the galaxy's mass. Only by observing across the entire spectrum can we truly understand what Andromeda is and how it works. Let's explore the gravitational forces that shape Andromeda and keep it stable over billions of years. A galaxy is a gravitationally bound system. Every star, every gas cloud, every particle of dark matter exerts gravity on every other component. The cumulative effect of all these gravitational interactions determines the galaxy's structure and evolution. At the largest scale, Andromeda sits in a gravitational potential well created primarily by its dark matter halo. This potential well is like a valley, and objects in the galaxy are rolling around in that valley. Objects near the center move quickly because the gravitational forces are strong. Objects in the outskirts move more slowly, but all are bound, unable to escape unless given sufficient energy. Within this overall potential, the disk of the galaxy rotates. The rotation provides centrifugal support against gravity. If the disk weren't rotating, it would collapse inward. The balance between gravity pulling inward and rotation flinging things outward maintains the disk's structure. This is why galaxies have disks in the first place. During the galaxy's formation, random motions of gas clouds collided and cancelled out, but the net angular momentum couldn't be lost. The gas settled into a rotating disk perpendicular to the angular momentum vector. The spiral arms arise from density waves, patterns that rotate through the disk at a different speed than the stars themselves. These waves are essentially sound waves, pressure waves moving through the disk. They're maintained by a phenomenon called swing amplification. Random density fluctuations in the disk get amplified by the galaxy's differential rotation and self-gravity. The amplified waves take the form of spiral patterns. These waves are long-lived, persisting for billions of years, even though individual stars pass through them relatively quickly. Bars, which both Andromeda and the Milky Way possess, arise from gravitational instabilities in the disk. Under certain conditions, the disk is unstable to the formation of a bar-shaped distortion. Once formed, the bar redistributes angular momentum, funneling gas inward or outward depending on orbital resonances. This affects star formation rates and patterns. Bars can also help supermassive black holes grow by channeling gas into the central regions. About 2/3 of spiral galaxies have bars, suggesting they're a natural outcome of disk galaxy evolution. Stellar orbits in galaxies are generally not closed ellipses like planetary orbits in the solar system. The gravitational potential of a galaxy is more complex, and orbits can be chaotic or quasi-periodic. Some stars follow rosette patterns, their orbits precessing over time. Others follow box orbits or loop orbits. These complex orbital patterns contribute to the overall shape and structure of the galaxy. In elliptical galaxies formed from mergers, the stellar orbits are highly randomized, which is why ellipticals have spheroidal shapes rather than flattened disks. Gravitational interactions between stars are generally weak because stars are so far apart. The typical separation between stars is several light years, while the stars themselves are only a few million kilometers across. The vast, empty space means direct collisions are essentially impossible. But weak, distant interactions do occur. Over millions of orbits, these tiny gravitational tugs add up, slowly changing stellar orbits. This process is called stellar relaxation, and it operates on timescales of billions to trillions of years. More significant are encounters with massive gas clouds. A star passing near a giant molecular cloud experiences a much stronger gravitational tug because the cloud contains millions of solar masses. These encounters can significantly alter stellar orbits. Computer simulations show that encounters with clouds can heat the stellar disk, increasing the random velocities of stars and puffing up the disk over time. This might explain why old stellar populations in galaxy disks have larger vertical scale heights than young populations. Satellite galaxies also perturb the main galaxy through tidal forces. As a satellite orbits Andromeda, its gravity raises tides in the disk, similar to how the Moon raises tides on Earth. These tides extract energy and angular momentum from the satellite's orbit, causing it to slowly spiral inward. At the same time, the tides transfer energy and angular momentum to the disk, heating it slightly. This is a slow process, but over billions of years, it can have measurable effects on both the satellite and the main galaxy. The stability of galaxies is a balance between self-gravity trying to make them collapse and various forms of support preventing collapse. In the disk, rotation provides support. In the bulge and halo, random stellar motions provide support, similar to how thermal motion of gas atoms provides pressure support against gravity. In dwarf galaxies dominated by dark matter, the dark matter's velocity dispersion provides support. Understanding this balance helps astronomers predict how galaxies evolve and how they respond to perturbations. Between the stars lies the interstellar medium, a thin soup of gas and dust that fills the galaxy. Most of this material is hydrogen, the simplest and most abundant element. Hydrogen exists in several forms throughout Andromeda. In the coldest molecular clouds, it forms molecular hydrogen. In warmer regions, it exists as neutral atomic hydrogen. Near hot stars, ultraviolet radiation ionizes it, stripping away the electrons and creating glowing H2 regions. The atomic hydrogen extends far beyond the visible stellar disk. Radio telescopes operating at a wavelength of 21 centimeters can map this neutral hydrogen. The resulting maps show that Andromeda's HI disk is warped and lopsided. One side extends significantly farther than the other. High-velocity clouds of hydrogen move through the halo at speeds that don't match the normal rotation pattern. These anomalies are signatures of past interactions with other galaxies. When galaxies pass near each other, tidal forces raise waves in the gas disks, much like the Moon raises tides in Earth's oceans. These tidal disturbances can persist for billions of years. The total mass of gas in Andromeda is substantial, roughly 8 billion solar masses in molecular form, plus several billion more in atomic hydrogen. That's enough raw material to build billions of additional stars. But star formation in Andromeda is proceeding at a relatively modest pace, creating only about 1 solar mass worth of stars per year. The Milky Way forms stars at roughly the same rate, despite being smaller. This suggests Andromeda has entered a more mature phase, having already converted most of its available gas into stars during earlier, more active periods. Dust represents only about 1% of the interstellar medium by mass, but it has outsized importance. Interstellar dust consists of tiny solid grains, predominantly carbon and silicates, with typical sizes around 1/10 of a micrometer. These grains form in the outer atmospheres of cool, evolved stars and in the ejecta from supernova explosions. They're blown into interstellar space by stellar winds and supernova shock waves. The grains scatter and absorb starlight, making distant objects appear fainter and redder than they actually are. This interstellar extinction complicates distance measurements and requires careful corrections. But dust also plays crucial roles in astrophysics. The surfaces of dust grains provide meeting places where atoms can stick and combine into molecules. Without dust, the rich molecular chemistry observed in space couldn't occur. Dust grains also shield the interiors of molecular clouds from harsh ultraviolet radiation, allowing them to remain cold and dense enough for gravitational collapse. And dust radiates in the infrared, revealing regions of star formation hidden from optical telescopes. Infrared observations of Andromeda light up the spiral arms and the star-forming ring, showing exactly where new stars are being born. Beyond the bright disk lies the halo, a roughly spherical distribution of old stars and globular clusters extending far into space. The stellar halo is faint and diffuse, containing only about 1% of the galaxy's stellar mass. These halo stars are Population 2, metal-poor relics from the early universe. They follow highly elliptical orbits that carry them far from the galactic plane before plunging back through it. Some halo stars might spend most of their time hundreds of thousands of light years from Andromeda's center, only occasionally passing through the visible galaxy. The halo also contains stellar streams, narrow rivers of stars stretched across the sky. These streams are the torn-apart remnants of dwarf galaxies and globular clusters that ventured too close to Andromeda. The galaxy's tidal forces pulled them apart, stripping away their outer stars. The stripped stars now follow the same orbit their parent object once traveled, creating a stream. By mapping these streams, astronomers can reconstruct Andromeda's merger history. Each stream represents a past meal, a smaller system that was consumed and digested. Globular clusters are the jewels of the halo. Andromeda hosts approximately 450 of these dense stellar cities. Each globular cluster contains hundreds of thousands of stars packed into a sphere only tens to hundreds of light years across. The clusters are among the oldest objects in the galaxy, having formed over 12 billion years ago when the universe was young. Their stars are metal poor, born from gas that contained mostly just hydrogen and helium. Studying globular clusters helps astronomers understand the early history of galaxy formation. The most massive globular clusters in Andromeda contain over 1 million stars. Mayal 2, also called G1, is the brightest globular cluster in Andromeda and one of the most luminous in the local group. It contains several million stars and is so massive that it likely has an intermediate mass black hole at its center. The cluster is roughly twice as luminous as Omega Centauri, the brightest globular in the Milky Way. If you could somehow visit a planet orbiting a star in the core of Mayal 2, your night sky would be filled with thousands of stars brighter than Venus appears from Earth. Darkness would be impossible. Globular clusters orbit Andromeda on highly elliptical paths. Some spend most of their time far out in the halo, only rarely passing through the main galaxy. Others have orbits that carry them through the disk regularly. When a globular cluster passes through the disk, interactions with gas clouds and stars can strip away its outer members. Over billions of years, these tidal interactions have whittled down some clusters, while others, in safer orbits, remain largely intact. The globular cluster system acts as a fossil record, preserving information about conditions in the early universe. Dark matter dominates Andromeda's mass. For every kilogram of normal matter, stars, planets, gas, and dust, there are roughly 6 kilograms of dark matter. We can't see dark matter directly because it doesn't emit, absorb, or scatter light. It doesn't interact electromagnetically at all. But we know it's there because of its gravitational effects. When astronomers measure how fast stars and gas orbit at various distances from Andromeda's center, they find something unexpected. The orbital speeds remain roughly constant, even far from the galactic center, rather than declining as they should if only visible matter were present. This flat rotation curve is the signature of dark matter. The dark matter must be distributed in an extended halo that reaches far beyond the visible galaxy. The halo is roughly spherical and extends out to at least 600,000 light-years from the center, perhaps farther. Most of Andromeda's gravitational mass resides in this dark matter halo, not in the stars and gas we can see. The visible galaxy is merely the tip of the iceberg, floating in a much larger sea of invisible matter. What is dark matter? Nobody knows for certain. It's one of the biggest mysteries in physics. It can't be made of normal atoms, because we've carefully measured the abundances of elements produced in the Big Bang, and there simply isn't enough normal matter to account for dark matter's gravitational effects. Dark matter must be something else entirely, some exotic particle or particles that barely interact with normal matter except through gravity. Physicists have proposed numerous candidates, weakly interacting massive particles called WIMPs, axions, sterile neutrinos, and more. Experiments deep underground and at particle accelerators are searching for these particles, but so far we haven't found them. Despite its mysterious nature, dark matter plays crucial roles in galaxy formation and evolution. Without dark matter, galaxies like Andromeda couldn't exist. The dark matter halo provides the gravitational scaffolding that holds the galaxy together. It also provides the gravity wells that captured gas in the early universe, allowing it to collapse and form stars. In a very real sense, dark matter is the foundation upon which all visible structure in the universe is built. We may not know what it is, but we know it's essential. Andromeda doesn't exist in isolation. It's accompanied by a family of smaller satellite galaxies, held in orbit by its immense gravity. At least 14 satellite galaxies are currently known, though more undoubtedly remain undiscovered. These satellites range from dwarf spheroidal galaxies containing a few billion stars down to ultra-faint dwarfs with only a few thousand stars. They're the survivors of galaxy formation, smaller structures that formed in the early universe and were later captured by Andromeda's gravitational pull. The two largest and most famous satellites are Messier 32 and Messier 110. M32 is a compact elliptical galaxy sitting only about 24,000 light-years from Andromeda's center, practically on top of the larger galaxy in cosmic terms. It measures roughly 8,000 light-years across and contains several billion stars. Despite its small size, M32 harbors a supermassive black hole at its center with a mass between 2 and 4 million times the Sun's mass. This is surprisingly large for such a small galaxy and suggests M32 might once have been much larger. Perhaps it was a more substantial galaxy that lost most of its stars during the close encounter with Andromeda that brought it to its current position. The tidal forces from Andromeda are slowly tearing M32 apart. The outer stars are being stripped away, pulled into Andromeda's halo. In a few billion years, M32 will likely be completely destroyed, its stars scattered and absorbed into Andromeda's stellar population. This process is happening throughout the local group. Large galaxies grow by cannibalizing smaller ones. It's galactic cannibalism, and it's a fundamental process in how galaxies evolve and grow over cosmic time. Messier 110, also catalogued as NGC 205, is larger but farther away, orbiting about 170,000 light-years from Andromeda's center. It's a dwarf spheroidal galaxy, elongated in shape and containing several billion stars. Like M32, it's being disrupted by Andromeda's tidal forces. Stellar streams connect M110 to Andromeda, visible in deep photographs as faint trails of stars stretching across space. These streams are stars that have been pulled away from the dwarf galaxy, now following similar orbits around Andromeda. Eventually, all of M110's stars will join Andromeda's halo. The other satellites are smaller and fainter. Many are ultra-faint dwarf galaxies, discovered only in recent decades using sensitive digital cameras on large telescopes. These tiny galaxies contain only thousands to hundreds of thousands of stars, making them incredibly difficult to detect. They're often dominated by dark matter, with dark matter outweighing visible matter by factors of hundreds or even thousands. Some are almost entirely dark, with just a handful of stars sprinkled through an extended dark matter halo. These dark matter-dominated dwarfs are valuable laboratories for studying dark matter because it's the dominant component and its effects are most easily measured. One intriguing feature of Andromeda's satellite system is that many of the satellites orbit in a thin plane, rather than being randomly distributed in all directions. This planar structure was initially puzzling and was even suggested as potential evidence contradicting the standard cosmological model. However, more recent thinking, particularly over the past few years, has converged on a likely explanation. The satellites probably formed from a single major merger event between 8 and 10 billion years ago. When a large galaxy collided with Andromeda, it was torn apart, and its debris formed the current generation of satellite galaxies. These tidal dwarf galaxies would naturally lie in a plane defined by the orbit of the original intruder. This explanation fits well with other evidence that Andromeda experienced a major merger in its past. Andromeda and the Milky Way are the two dominant galaxies in our local group, and comparing them reveals both similarities and differences. Both are large barred spiral galaxies with similar structures. Both have central supermassive black holes, extensive spiral arms, stellar halos, and families of satellite galaxies. In many ways, they're twin galaxies, born at similar times from similar conditions. But Andromeda is bigger. Its diameter substantially exceeds the Milky Way's. It contains 2 to 3 times as many stars. Recent mass estimates, incorporating the latest data from the Gaia spacecraft and other sources, suggest Andromeda's total mass, including dark matter, is around 1.5 to 2 trillion solar masses, while the Milky Way weighs in at approximately 1 to 1.5 trillion solar masses. There was a brief period around 2018 and 2019 when some studies suggested the Milky Way might actually be more massive, but subsequent analyses have walked back those claims. Andromeda remains the more massive of the two, though not by an enormous margin. One intriguing feature of Andromeda's satellite system is that many of the satellites orbit in a thin plane rather than being randomly distributed in all directions. This planar structure was initially puzzling and was even suggested as potential evidence contradicting the standard cosmological model. However, more recent thinking, particularly over the past few years, has converged on a likely explanation. The satellites probably formed from a single major merger event between 8 and 10 billion years ago. When a large galaxy collided with Andromeda, it was torn apart, and its debris formed the current generation of satellite galaxies. These tidal dwarf galaxies would naturally lie in a plane defined by the orbit of the original intruder. This explanation fits well with other evidence that Andromeda experienced a major merger in its past. Andromeda and the Milky Way are the two dominant galaxies in our local group, and comparing them reveals both similarities and differences. Both are large barred spiral galaxies with similar structures. Both have central supermassive black holes, extensive spiral arms, stellar halos, and families of satellite galaxies. In many ways, they're twin galaxies, born at similar times from similar conditions. But Andromeda is bigger. Its diameter substantially exceeds the Milky Way's. It contains 2 to 3 times as many stars. Recent mass estimates, incorporating the latest data from the Gaia spacecraft and other sources, suggest Andromeda's total mass, including dark matter, is around 1.5 to 2 trillion solar masses, while the Milky Way weighs in at approximately 1 to 1.5 trillion solar masses. There was a brief period, around 2018 and 2019, when some studies suggested the Milky Way might actually be more massive, but subsequent analyses have walked back those claims. Andromeda remains the more massive of the two, though not by an enormous margin. Andromeda's central black hole is substantially more massive than the Milky Way's, roughly 35 times heavier. Its stellar halo is more extensive and shows more evidence of past mergers. The major collision about 800 million years ago left its mark in stellar streams, disturbed gas distributions, and asymmetries in the spiral structure. The Milky Way has also experienced mergers with smaller galaxies, notably the Sagittarius dwarf elliptical galaxy, which is currently in the process of being torn apart as it passes through our galaxy. But Andromeda's merger history appears more violent. Star formation rates tell an interesting story. Despite being larger and more massive, Andromeda is currently forming stars at roughly the same rate as the Milky Way, around 1 solar mass per year. This suggests Andromeda has already gone through its most active star-forming phase and is now in a more mature, quieter period. The Milky Way is still relatively active. Over cosmic timescales, both galaxies are gradually converting their remaining gas into stars. But the process is slowing as the gas reservoirs deplete. If you could view both galaxies from a distance, Andromeda would appear larger and somewhat brighter, but both would be magnificent. Two grand spiral structures glowing against the darkness, island universes separated by the void of intergalactic space. But that separation is temporary. Gravity is pulling them together, and in the cosmic future, they'll merge into one. Andromeda and the Milky Way are approaching each other at approximately 110 kilometers per second, or about 68 miles per second. That's roughly 400,000 kilometers per hour, or 250,000 miles per hour. At this speed, you could circle Earth's equator in just over 6 minutes. Yet despite this tremendous velocity, the distance between the galaxies is so vast that the collision will take billions of years to unfold. In approximately 4.5 billion years, Andromeda and the Milky Way will experience their first close encounter. But calling it a collision is somewhat misleading. When galaxies merge, the stars themselves almost never collide. Space is mostly empty, and stars are separated by vast distances. The actual probability of two stars colliding during a galaxy merger is essentially zero. What does collide is the gas. Gas clouds from both galaxies will slam into each other, compressing and heating. These collisions will trigger intense bursts of star formation, creating millions of new stars in a relatively short period. Gravitationally, the encounter will be violent. The orderly spiral structures of both galaxies will be disrupted. Stars will be flung into new, chaotic orbits. Some will gain enough energy to escape the merging system entirely, becoming intergalactic wanderers drifting through the void with no galaxy to call home. Others will sink toward the center. The two supermassive black holes will spiral inward, eventually merging into a single, even more massive black hole. This merger will release tremendous energy in the form of gravitational waves, ripples in space-time, that will propagate across the universe at the speed of light. Andromeda and the Milky Way are approaching each other at approximately 110 kilometers per second, or about 68 miles per second. That's roughly 400,000 kilometers per hour, or 250,000 miles per hour. At this speed, you could circle Earth's equator in just over 6 minutes. Yet despite this tremendous velocity, the distance between the galaxies is so vast that the collision will take billions of years to unfold. In approximately 4.5 billion years, Andromeda and the Milky Way will experience their first close encounter. But calling it a collision is somewhat misleading. When galaxies merge, the stars themselves almost never collide. Space is mostly empty, and stars are separated by vast distances. The actual probability of two stars colliding during a galaxy merger is essentially zero. What does collide is the gas. Gas clouds from both galaxies will slam into each other, compressing and heating. These collisions will trigger intense bursts of star formation, creating millions of new stars in a relatively short period. Gravitationally, the encounter will be violent. The orderly spiral structures of both galaxies will be disrupted. Stars will be flung into new, chaotic orbits. Some will gain enough energy to escape the merging system entirely, becoming intergalactic wanderers drifting through the void with no galaxy to call home. Others will sink toward the center. The two supermassive black holes will spiral inward, eventually merging into a single, even more massive black hole. This merger will release tremendous energy in the form of gravitational waves, ripples in space-time that will propagate across the universe at the speed of light. The merger won't be instantaneous. After the first encounter, the two galaxies will pass through each other, then swing back due to their mutual gravitational attraction. They'll collide again and again, each passage further scrambling their stars and gas. This dance will continue for several billion years. Eventually, after multiple passes, the system will settle down into a single merged galaxy. Astronomers have playfully dubbed this future galaxy Milkomeda, or Milkdromeda. It will be a giant elliptical galaxy, a smoothly distributed ball of stars lacking the spiral structure of either parent. Elliptical galaxies are thought to form primarily through major mergers of spiral galaxies. When spirals collide, their orderly disk structures are destroyed. The stars, which were orbiting in roughly the same plane, get scattered onto orbits with random orientations. The result is a spheroidal distribution. Star formation typically shuts down quickly after the merger, because the violent gravitational interactions heat the remaining gas, puffing it up and making it too diffuse to collapse and form new stars. Ellipticals are often called red and dead because they contain primarily old red stars with little ongoing star formation. What about Earth? Our planet will likely survive the actual collision, though its orbit may shift because of gravitational tugs from passing stars. By the time Andromeda and the Milky Way merge, however, the Sun will already have entered its red giant phase. Roughly 5 billion years from now, it will exhaust the hydrogen in its core and start fusing hydrogen in a surrounding shell. This will cause its outer layers to swell enormously. The red giant Sun may grow large enough to swallow Mercury and Venus entirely. Earth could linger on the fringes of this expanded atmosphere, scorched, airless, and lifeless, but still physically intact. If Earth does survive in some form, the view during the merger will be spectacular. The two galaxies will fill the sky with stars, gas clouds, and glowing nebulae. New stars will blaze to life in enormous numbers. The night sky will be brilliant with light, far brighter than anything we see today. Eventually, once the merger completes, the sky will be uniformly filled with stars rather than showing the Milky Way band we see now. It will be one of the most beautiful cosmic sights imaginable, though sadly, no humans will likely be around to witness it. Not all stars in Andromeda are the same. The galaxy contains stars of vastly different ages, masses, and chemical compositions. Astronomers classify stars into populations based on their properties. Population 1 stars are relatively young and metal-rich. In astronomical parlance, metals are any elements heavier than hydrogen and helium. These stars formed from gas that had been enriched by previous generations of stellar death. When massive stars explode as supernovae, they forge heavy elements in their cores and blast them into space. This enriched material mixes with the interstellar medium and becomes part of the next generation of stars. Population 1 stars are found primarily in the galactic disk and spiral arms. They include hot blue O and B stars, medium stars like our Sun, and small red dwarfs. These stars contain roughly 2% heavy elements by mass, similar to the Sun's composition. The presence of heavy elements affects stellar structure and evolution in subtle but important ways. It also makes planets possible. Rocky planets like Earth are built from heavy elements: carbon, oxygen, silicon, iron, and others. Without previous generations of stars to create these elements, terrestrial planets couldn't exist. Population. 2 stars are older and metal-poor. They formed in the early history of the galaxy, when the universe contained mostly just hydrogen and helium. Little or no heavy element enrichment had occurred yet. These stars typically contain less than 1/10 the heavy element content of the Sun, some even less. Population 2 stars dominate the galactic bulge and halo. They include red giants, horizontal branch stars, and the ancient stars in globular clusters. Some of these stars are over 12 billion years old, born when the universe was less than 2 billion years old. By studying population 2 stars, astronomers can probe the early history of Andromeda. Their chemical compositions preserve information about conditions in the primordial gas from which they formed. Their ages tell us when significant star formation occurred. Their distributions and velocities reveal how the galaxy assembled itself. In essence, these old stars are fossils, carrying information about a time long past. Galactic archaeology, the study of stellar populations to understand galaxy history, has become a major research field in modern astronomy. There's also a hypothetical population 3, the very first stars to form in the universe. These would have been made entirely of hydrogen and helium, with absolutely zero heavy elements, because no previous stars existed to create them. Computer simulations suggest population 3 stars were massive, perhaps hundreds of times the mass of the Sun. They would have been incredibly luminous and short-lived, burning through their fuel in only a few million years before exploding as supernovae or collapsing directly into black holes. These first supernovae seeded the universe with the first heavy elements, enabling all subsequent stellar generations. No population 3 stars have ever been observed. They all died billions of years ago. But their existence is inferred from the chemistry of population 2 stars, which show evidence of heavy element enrichment at very low levels. Some globular clusters contain stars with heavy element abundances, suggesting they formed from gas, enriched by only one or a few supernova explosions, possibly from population 3 stars. The search for evidence of population 3 continues, using observations of the most metal-poor stars and the most distant galaxies visible. Andromeda's stellar populations tell a story of assembly and evolution. The old halo and bulge represent the ancient past, formed during the initial collapse of the proto-galaxy. The disk built up more gradually through continued gas accretion and star formation. The spiral arms are sites of ongoing star formation representing the galaxy's present activity. And scattered throughout are stars of intermediate ages, filling in the history between past and present. This temporal diversity makes Andromeda a living museum, displaying stars from every era of cosmic history. Everything we know about Andromeda comes from observation. Astronomers have studied the galaxy across the entire electromagnetic spectrum, from radio waves through visible light to X-rays and gamma rays. Each wavelength range reveals different physical processes and structures. In visible light, we see the stars themselves, billions of individual suns contributing their photons to the integrated glow. Blue light comes from young, hot stars in the spiral arms. Red light comes from older, cooler stars in the bulge and halo. By imaging in different colors and measuring the brightnesses, astronomers can determine stellar populations and map out where different types of stars live. Ultraviolet observations reveal the hottest stars, those young, massive O and B stars with surface temperatures exceeding 20,000 degrees. These stars emit most of their light in ultraviolet wavelengths invisible to our eyes. The Galaxy Evolution Explorer satellite, GALEX, mapped Andromeda in ultraviolet light, highlighting regions of active star formation. The images revealed the star-forming ring at 32,000 light-years radius in stunning detail, along with numerous other bright clusters and associations of young stars in the spiral arms. Infrared observations pierce through interstellar dust to reveal hidden structures. Dust blocks visible light, but is transparent to longer infrared wavelengths. The Spitzer Space Telescope and other infrared missions have mapped Andromeda's dust distribution, showing where cold molecular clouds concentrate. Infrared light also traces older, cooler, stellar populations. By combining optical and infrared data, astronomers build complete pictures of stellar demographics, determining how many stars of each type exist and where they're located. Radio observations provide unique information. The 21-centimeter line of neutral hydrogen allows radio telescopes to map the distribution and motion of HI gas throughout the galaxy and into the halo. These maps reveal the warped, lopsided disk and the high-velocity clouds suggesting past interactions. Radio observations also detect molecular gas through emission from carbon monoxide, which traces the coldest, densest clouds where star formation occurs. And radio continuum emission, produced by supernova remnants and active galactic nuclei, reveals high-energy processes invisible at other wavelengths. X-ray telescopes like Chandra see the hottest and most energetic phenomena. X-ray observations reveal the supermassive black hole at the galaxy's center, showing occasional flares when it swallows material. They detect binary star systems where a normal star orbits a compact object, either a neutron star or stellar mass black hole. Gas, stripped from the normal star, falls onto the compact object, heating to millions of degrees and emitting X-rays. Chandra has catalogued hundreds of X-ray binary systems in Andromeda. X-rays also trace hot gas in the halo, heated by supernova explosions and stellar winds, temperatures exceeding 1,000,000 degrees. One of the most ambitious projects to study Andromeda was the Panchromatic Hubble Andromeda Treasury, or FAT. Using the Hubble Space Telescope, astronomers imaged a large section of Andromeda's disk in exquisite detail, resolving individual stars. The resulting image contains over 100 million resolved stars. By measuring the brightnesses and colors of these stars, the team determined their ages and chemical compositions. This allowed them to map out star formation history across the galaxy, showing where and when stars formed over the past billions of years. The FAT survey revealed that star formation in Andromeda has varied in both space and time, with periods of intense activity interspersed with quieter epochs. Computer simulations complement observations. Astronomers use supercomputers to model galaxy formation and evolution. They simulate the collapse of dark matter halos, the infall of gas, star formation, supernova feedback, and galaxy mergers. By comparing simulated galaxies to observations, They test their understanding of the physical processes at work. Simulations of Andromeda's past mergers have reproduced many observed features, including stellar streams and asymmetries in the disk. These simulations help astronomers interpret what they see and predict what they might find with future observations. Let's take a moment to zoom into a single region of Andromeda and appreciate the layers of structure. Imagine focusing on one of the bright star-forming regions in a spiral arm. This region is a molecular cloud complex, several hundred light-years across. Within it, dense cores are collapsing under gravity. Each core will birth a star, or perhaps a small cluster of stars. Let's zoom further into one collapsing core. As the gas collapses, it heats up. Conservation of angular momentum causes it to form a rotating disk around the forming star. This is a protoplanetary disk, the birthplace of planets. Within this disk, dust grains collide and stick together. Over millions of years, these grains grow into pebbles, then boulders, then planetesimals kilometers across. Planetesimals collide and merge, building up protoplanets. Eventually, a few bodies dominate, clearing out their orbital zones and becoming full-fledged planets. Imagine this particular star forms a system similar to our solar system. A few rocky planets close in, where temperatures were high enough during formation that only rock and metal could condense. Further out, beyond what astronomers call the snow line, temperatures were low enough that water, ice, and other volatiles could condense. Here, planets grew much larger because they could incorporate ices in addition to rock and metal. These became gas giants, accumulating thick atmospheres of hydrogen and helium. And scattered throughout the system are asteroids and comets, the leftover building blocks that never got incorporated into planets. One of the rocky planets orbits in the habitable zone, the region where liquid water can exist on the surface. Let's say this planet is similar to Earth, roughly 12,700 kilometers or about 7,900 miles in diameter. It has continents, oceans, an atmosphere. Over time, chemistry on the planet's surface becomes increasingly complex. Organic molecules form, perhaps in tide pools or around hydrothermal vents. Eventually, somehow, these molecules organize into something that can replicate itself. Life begins. This entire story, from galaxy to star-forming region, to molecular cloud, to protoplanetary disk, to planet to life, could be playing out right now in Andromeda. Given the immense stellar population, such processes are likely occurring billions of times simultaneously across the galaxy. Each star is a potential Sunday. Each planet is a potential world. We can't see these planets directly. They're too small and too far away, lost in the glare of their parent stars. But statistically, they must exist. Planet formation appears to be a natural consequence of star formation. Everywhere we look in our own galaxy, we find planets. There's no reason Andromeda should be different. This raises profound questions. How common is life? Is it rare, arising only under very specific conditions? Or does it emerge readily wherever the environment allows? We don't know. We have only one example: Earth. Every living thing on our planet shares a common ancestor. So life arose only once here, or if it arose multiple times, only one lineage survived. We might discover microbial life elsewhere in our solar system, on Mars or in the subsurface oceans of Europa or Enceladus. That would suggest life is relatively common. Or we might find nothing, suggesting it's rare. Either answer will be profound. And what about intelligent life? Life with technology, capable of altering its environment and eventually reaching for the stars. Intelligence might be common, or it might be vanishingly rare. Perhaps it emerges often, but self-destructs quickly. Perhaps it's stable but stays quiet, making it hard to detect. Perhaps we're alone, the only conscious observers in the entire observable universe. We don't know. The question of extraterrestrial intelligence remains unanswered despite decades of searching. Andromeda's vast stellar population makes it statistically one of the best places for life to exist. But we can't confirm it from here. The distance is simply too great. Let's talk about what we can't see. Despite all our observational advances, there's much about Andromeda that remains hidden. We can't resolve individual planets. The angular separation between a planet and its star, as seen from our location, is far too small for current telescopes to distinguish. Even the largest telescopes, aided by adaptive optics or interferometry, can't pick out Earth-sized planets around stars in Andromeda. The James Webb Space Telescope, our newest and most powerful observatory, still can't do it. The light from the star overwhelms the faint reflected light from the planet. We also can't detect individual asteroids, comets or moons. These small bodies are utterly invisible at Andromeda's distance. Even large moons, objects hundreds or thousands of kilometers across, remain hidden. We can infer that such objects must exist based on what we see in our own solar system, but we can't observe them directly. The scale is simply too vast. Everything smaller than a star is effectively invisible. And what about intelligent life? Life with technology capable of altering its environment and eventually reaching for the stars. Intelligence might be common, or it might be vanishingly rare. Perhaps it emerges often but self-destructs quickly. Perhaps it's stable but stays quiet, making it hard to detect. Perhaps we're alone, the only conscious observers in the entire observable universe. We don't know. The question of extraterrestrial intelligence remains unanswered despite decades of searching. Andromeda's vast stellar population makes it statistically one of the best places for life to exist. But we can't confirm it from here. The distance is simply too great. Let's talk about what we can't see. Despite all our observational advances, there's much about Andromeda that remains hidden. We can't resolve individual planets. The angular separation between a planet and its star, as seen from our location, is far too small for current telescopes to distinguish. Even the largest telescopes, aided by adaptive optics or interferometry, can't pick out Earth-sized planets around stars in Andromeda. The James Webb Space Telescope, our newest and most powerful observatory, still can't do it. The light from the star overwhelms the faint reflected light from the planet. We also can't detect individual asteroids, comets, or moons. These small bodies are utterly invisible at Andromeda's distance. Even large moons, objects hundreds or thousands of kilometers across, remain hidden. We can infer that such objects must exist based on what we see in our own solar system, but we can't observe them directly. The scale is simply too vast. Everything smaller than a star is effectively invisible. We can't see individual habitable zone planets. We can't search for biosignatures, signs of life in planetary atmospheres. The techniques that work for exoplanets in our own galaxy don't work at Andromeda's distance. We're limited to studying the integrated light from millions of stars. We can resolve individual stars in some cases, but planets remain beyond reach. This is frustrating because it means we can't answer one of the most interesting questions: does life exist in Andromeda? We can speculate, but we can't know. Even for stars, our knowledge is incomplete. We can resolve bright, massive stars. We can see red giants and supergiants. But the small, faint stars, the red dwarfs that make up the majority of stars in any galaxy, are too dim to see individually in Andromeda. We infer their existence from the overall mass and luminosity of the galaxy, but we can't count them one by one. Similarly, stellar remnants like white dwarfs, neutron stars, and stellar mass black holes are mostly invisible unless they're in binary systems where interactions with a companion star make them detectable. Dark matter remains completely invisible. We know it's there from its gravitational effects, but we can't see it or directly measure its distribution. We infer the dark matter halo's shape and extent from rotation curves and from the motions of satellite galaxies, but these are indirect methods. The true nature of dark matter, what it's made of, how it's distributed on small scales, remains mysterious. Andromeda is large by local standards, but the universe contains galaxies that dwarf it. To understand Andromeda's place in the cosmic hierarchy, we need to compare it to other galaxies. In our local group of roughly 50 galaxies, Andromeda is the largest. The Milky Way is second. But venture beyond the local group into larger galaxy clusters, and you find giants that make Andromeda look modest. Take Messier 87, an enormous elliptical galaxy in the Virgo cluster. M87 spans about 120,000 light-years, actually smaller than Andromeda in diameter. But it's far more massive, containing several trillion stars, significantly more than Andromeda's population. M87 is also famous for its supermassive black hole. In April of 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole showing the shadow of M87's monster. That black hole weighs approximately 6.5 billion solar masses, roughly 46 times more massive than Andromeda's central black hole. The black hole's accretion disk and jet make M87 one of the most powerful radio sources in the sky. Then there are the true behemoths. IC 1011, one of the largest galaxies known, stretches about 1 to 2 million light-years across. Early measurements suggested 6 million light-years, but those figures came from very deep photographic exposures that included extremely faint outer regions. More careful modern measurements place the diameter closer to 1 to 2 million light-years for the main body, still enormous. IC 1011 contains roughly 100 trillion stars, about 100 times Andromeda's count. This galaxy grew to such immense size by cannibalizing its neighbors. It sits at the center of the Abell 2029 cluster, and its gravity has pulled in and absorbed dozens of smaller galaxies over billions of years. These ultra-giant ellipticals are relatively rare. Most galaxies are small. Dwarf galaxies outnumber large galaxies by a huge margin. The Milky Way and Andromeda are actually quite large by cosmic standards, bigger than 95% of all galaxies. Only about 5% of galaxies are larger. Yet those rare giants can be astonishingly huge, putting even Andromeda to shame. Comparing Andromeda to these giants provides perspective. Andromeda is large, but not uniquely so. It's an important galaxy for us because it's nearby. We can study it in detail impossible for more distant galaxies. We can resolve individual stars, map out structure on small scales, and trace its history with precision. More distant galaxies appear as fuzzy blobs even in our best images. We can measure their overall properties, total luminosity, mass, color, but we can't see the details. Andromeda gives us a detailed look at a large spiral galaxy, something we can't achieve with our own Milky Way because we're inside it. Here's something to contemplate. When you look at Andromeda, you're seeing it as it was 2.5 million years ago. The light you're seeing left that galaxy before modern humans evolved. If aliens in Andromeda pointed a telescope at the Milky Way right now, they'd see our galaxy as it was 2.5 million years ago. They wouldn't see the present, they'd see the past. This is true for everything in astronomy. We never see the present state of distant objects. We always see their past. For nearby objects, this doesn't matter much. The sun is 8 light minutes away, so we see it as it was 8 minutes ago. The moon is about 1¼ light seconds away. The delay is negligible. But for Andromeda, the delay is substantial. Stars have been born and died in Andromeda during the time it took their light to reach us. The galaxy has continued evolving, changing, while we wait for the updated information to arrive. This means there's a fundamental limit to how quickly we can learn about Andromeda. If something happens there today, we won't know about it for 2.5 million years. If we somehow sent a signal to Andromeda, it would take 2.5 million years to arrive. A reply would take another 2.5 million years to return. Communication would be impossible on any practical timescale. This isolation is a consequence of the speed of light being finite. Information can't travel faster than light, and even at light speed, crossing cosmic distances takes an eternity. This also means that Andromeda's current state is unknown to us. We can extrapolate based on what we know about galactic evolution. We can make educated guesses, but we can't observe it directly. The present Andromeda exists out there right now, 2.5 million years ahead of what we see. It's continuing to evolve, forming new stars, experiencing supernova explosions, accreting satellite galaxies. All of this is happening in Andromeda's present, but we won't see it until the far future. It's a strange consequence of relativity and the vastness of space. Could life exist in Andromeda right now? Almost certainly yes, if we're talking about simple microbial life. The building blocks of life, carbon, hydrogen, nitrogen, oxygen, phosphorus, are abundant throughout the universe. Andromeda contains all these elements, forged in stellar cores and scattered through space by supernovae. Planets orbit its innumerable suns, and some must be inhabitable zones where conditions allow liquid water. On Earth, life appeared relatively quickly after the planet cooled enough to support it. The oldest evidence of life dates back about 3.8 billion years, only about 700 million years after Earth formed. This suggests that life, at least simple microbial life, arises readily when conditions allow. If that's generally true, then many planets in Andromeda probably host life. We're talking potentially billions of living worlds, each with its own unique biosphere, its own evolutionary history. But intelligent life is another question. Intelligence, particularly technological intelligence, capable of altering environments and building civilizations, might be much rarer. On Earth, simple life existed for about 3 billion years before complex multicellular life appeared. Then it took another 500 million years for intelligence to evolve. Humans emerged only in the last few 100,000 years. If the jump to intelligence is difficult and requires specific conditions, it might be rare. Perhaps most life remains simple, microbial, never evolving the complexity needed for sentience. Or perhaps intelligence is common but self-limiting. Technological civilizations might tend to destroy themselves shortly after developing advanced technology. Nuclear weapons, climate change, artificial intelligence risks. There are many potential filters that could prevent civilizations from lasting long enough to become noticeable on cosmic scales. This is one proposed solution to the Fermi paradox, the question of why we haven't detected signs of alien civilizations, despite the apparent abundance of habitable planets. Maybe civilizations exist, but burn out quickly, leaving the galaxy mostly empty of intelligence, despite being filled with life. Another possibility is that intelligence is common, but stays quiet. advanced civilizations might learn that broadcasting their presence is dangerous, attracting unwanted attention. Or they might communicate in ways we haven't thought of yet, using technologies or methods we can't detect. Or they might simply not be interested in contacting others. They could be focused inward, exploring virtual worlds or higher states of consciousness, ignoring the physical universe around them. If intelligent civilizations exist in Andromeda, we'll probably never know. The distance is too great for communication or travel. Any signal they send would take 2.5 million years to reach us. They'd be receiving signals from us showing Earth as it was when early hominids walked the savannah. It's unlikely they'd recognize those signals as signs of intelligence. And by the time our current signals reach them, humanity might have evolved into something unrecognizable or might not exist at all. The timescales involved make meaningful contact essentially impossible. Yet there's something profound about the possibility. If life exists in Andromeda, even if we can never contact it, it means we're not alone in the universe. The cosmos isn't dead. It's teeming with complexity, diversity, perhaps even consciousness. Somewhere among those countless suns, perhaps beings are looking up at their sky, seeing the Milky Way as a faint smudge, and wondering if anyone else is out there. The universe could be full of questions looking for answers, minds contemplating their existence. We're connected not by communication or proximity, but by the shared experience of being conscious entities trying to understand our place in a vast cosmos. One of the most ambitious projects to study Andromeda was the Panchromatic Hubble Andromeda Treasury, or FAT. Using the Hubble Space Telescope, astronomers imaged a large section of Andromeda's disk in exquisite detail, resolving individual stars. The resulting image contains over 100 million resolved stars. By measuring the brightnesses and colors of these stars, the team determined their ages and chemical compositions. This allowed them to map out star formation history across the galaxy, showing where and when stars formed over the past billions of years. The FAT survey revealed that star formation in Andromeda has varied in both space and time, with periods of intense activity interspersed with quieter epochs. Computer simulations complement observations. Astronomers use supercomputers to model galaxy formation and evolution. They simulate the collapse of dark matter halos, the infall of gas, star formation, supernova feedback, and galaxy mergers. By comparing simulated galaxies to observations, they test their understanding of the physical processes at work. Simulations of Andromeda's past mergers have reproduced many observed features, including stellar streams and asymmetries in the disk. These simulations help astronomers interpret what they see and predict what they might find with future observations. Let's think more carefully about what will happen when Andromeda and the Milky Way finally collide. Computer simulations have modeled this event in detail. About 3 to 4 billion years from now, Andromeda will fill our night sky. It will no longer be a faint smudge, but a brilliant structure spanning vast angular scales. The spiral arms will be visible to the naked eye. Individual bright stars and star clusters will stand out. It will be a magnificent sight, assuming Earth still exists and has clear skies. The first close passage will occur about 4.5 billion years from now. The two galaxies will interpenetrate, passing through each other. Gravitational interactions will distort both galaxies, pulling out long tidal tails of stars. These tails will stretch for hundreds of thousands of light years, rivers of stars streaming through space. The ordered spiral structures will be disrupted. The disks will warp and buckle. Star formation will explode as gas clouds collide, creating brilliant bursts of blue light from newly formed massive stars. After the first passage, the two galaxies will separate again, moving apart due to their velocities. But gravity will slow them down, stop them, and pull them back together. A second collision will occur, then a third. Each collision will further scramble the stellar orbits and consume more gas in starbursts. The simulations show that it typically takes about 3 to 5 billion years for the merger to complete after the first encounter. During this time, the two galaxies will repeatedly pass through each other, each time looking different, each time more chaotic. The supermassive black holes from each galaxy will sink toward the center of the merging system through a process called dynamical friction. As a black hole moves through a sea of stars, the stars behind it are gravitationally accelerated, stealing momentum from the black hole and causing it to slow down and sink. Eventually, the two black holes will form a binary system, orbiting each other while surrounded by stars. The orbit will gradually decay as the binary emits gravitational waves, carrying away energy and angular momentum. Finally, in a cataclysmic event lasting perhaps just a few minutes, the two black holes will spiral together and merge. The merger will release more energy in gravitational waves than all the stars in the observable universe emit as electromagnetic radiation during the same time. The space-time around the black holes will oscillate wildly, creating powerful gravitational wave signals that will propagate across the cosmos at light speed. If human descendants are still around and have gravitational wave detectors, they'll record this event with exquisite precision, learning about the masses and spins of the merging black holes and testing general relativity in the most extreme conditions. The end result, several billion years after the first encounter, will be a giant elliptical galaxy. Milkymeda will contain roughly 1.5 to 2 trillion stars, nearly all the stars from both parent galaxies. Some stars will have been ejected entirely, flung out at high speeds by close gravitational encounters. These intergalactic stars will wander through the void, forever separated from any galaxy. But most stars will remain bound, settling into a roughly spherical distribution. The merged galaxy will be one of the largest members of the local group, dominated by old red stars with little ongoing star formation. Andromeda's existence isn't an isolated fact. It's part of a larger story, the story of how structure formed in the universe. In the beginning, just after the Big Bang, the universe was remarkably smooth and uniform. Tiny quantum fluctuations during inflation created slight density variations, regions that were very slightly denser or less dense than average. These variations were incredibly small, only 1 part in 100,000, but they were enough. As the universe expanded and cooled, gravity amplified these small variations. Denser regions attracted surrounding matter, becoming denser still. Less dense regions lost matter to their surroundings, becoming voids. Over millions of years, the first structures formed. These were dark matter halos, gravitationally bound clumps of dark matter. The dark matter couldn't collapse further because it doesn't interact electromagnetically. It doesn't radiate energy away. But normal matter, hydrogen and helium gas, could cool by radiating. The gas fell into the dark matter halos and eventually collapsed enough to form the first stars. These first stars, the hypothetical population 3, were probably massive and short-lived. They exploded as supernovae, enriching the surrounding gas with heavy elements. Subsequent generations of stars formed from enriched gas, creating population 2 stars. Gradually, these early stellar systems merged together, building larger structures. Small galaxies merged to form bigger galaxies. Some of these mergers spun up rotating disks, creating spiral galaxies. Others created ellipticals, Andromeda formed through this process. It assembled over billions of years through mergers and gas accretion. The evidence is written in its structure, in the stellar streams from disrupted satellites, in the mix of stellar populations, in the warped gas disk. Andromeda is still growing, still consuming smaller galaxies. Over trillions of years, structures will continue evolving, though at an ever slower pace as the universe expands and galaxies become isolated. In a sense, Andromeda is typical. It formed, like most galaxies, through hierarchical assembly in a universe dominated by dark matter. But it's also special to us because it's nearby. It's close enough to study in detail, yet far enough to see as a complete object. It gives us insights into galaxy formation and evolution that we can't get from our own galaxy, where we're embedded inside and can't see the whole structure. Andromeda is a laboratory for understanding how galaxies work. We've covered an immense amount of information, but let's step back and reflect on scale. Crossing Andromeda at light speed would require the same amount of time as its diameter in light years. The total number of worlds throughout the galaxy might be in the tens of trillions or hundreds of trillions. The galaxy has existed for about 12 billion years, forming shortly after the Big Bang. It will continue existing for trillions of years to come, though eventually merging with the Milky Way. Now think about yourself. You're a human being, approximately 2 meters or 6 feet tall. You live on a planet about 12,700 kilometers, or 7,900 miles in diameter. That planet orbits a star in a galaxy of hundreds of billions of stars. And that galaxy is tiny compared to Andromeda. You're separated from Andromeda by 2.5 million light years, a distance so vast that the numbers lose meaning. Yet here you are, aware of Andromeda, able to contemplate its existence, to measure its properties, to understand what it is. This is extraordinary. The universe is vast beyond comprehension, yet conscious beings exist within it, able to understand it. We're made of atoms, forged in stars. We're star stuff, as Carl Sagan said. The carbon in our bodies, the oxygen we breathe, the calcium in our bones, all of it was created in stellar cores and scattered through space by supernova explosions. We're literally made of the same material as Andromeda. We're not separate from the cosmos. We're part of it. Andromeda's scale is humbling. It reminds us how small we are, how brief our lives are compared to cosmic timescales. But it also inspires wonder. The fact that we can study something so distant, so large, so ancient, speaks to human curiosity and ingenuity. We've gone from thinking the universe was just the visible stars above our heads to measuring galaxies millions of light years away. That's an incredible achievement. Understanding Andromeda changes how we see ourselves. We're residents of a mid-sized spiral galaxy in a local group of about 50 galaxies. Andromeda is our largest neighbor, and we're gravitationally bound to it. In a sense, Andromeda is part of our cosmic neighborhood. The atoms that currently reside there follow their own evolutionary paths, shaped by the same physical laws that govern our galaxy. But on human timescales, Andromeda is distant and separate. We can observe it, study it, admire it, but we can't visit it. The distance is too great. Even if we develop technology to travel at significant fractions of light speed, the journey would take millions of years. It's effectively unreachable. This isolation is sobering. The universe is filled with wonders, but most of them are forever beyond our grasp. We can see them, measure them, understand them intellectually, but we can't touch them. Yet there's beauty in this isolation. The universe isn't a small, cozy place where everything is accessible. It's vast, filled with countless galaxies, each containing billions or trillions of stars. Andromeda is just one of roughly 2 trillion galaxies in the observable universe. Each galaxy is a world unto itself, evolving over billions of years according to the laws of physics. And we, from our tiny corner, can observe and understand them all. We've journeyed across 2.5 million light-years tonight. We've explored this immense galactic structure. We've examined its spiral arms, central bulge, supermassive black hole, and halo of dark matter. We've seen how astronomers measure such vast distances using the cosmic distance ladder. We've explored the lives and deaths of stars within the galaxy. We've discussed magnetic fields, cosmic rays, and the various types of nebulae that light up its structure. We've compared Andromeda to the Milky Way and found it larger but similar. We've examined its satellite galaxies being slowly torn apart and absorbed. We've looked at gravitational dynamics and orbital mechanics that keep this vast structure stable. We've contemplated the possibility of life among its trillion suns and countless worlds, even though we may never be able to confirm it from our distant vantage point. We've contemplated the possibility of life among its suns and countless worlds, even though we may never be able to confirm it from our distant vantage point. The true scale of Andromeda isn't just about numbers, though the numbers are staggering. It's about what those numbers represent. It's about complexity and diversity on scales beyond human comprehension. It's about a structure so vast that light takes longer to cross it than humans have existed as a species. It's about 1 trillion opportunities for stars and planets, and maybe life. It's about a dynamic, evolving system that has been forming stars for 12 billion years and will continue for billions more. Andromeda is out there right now, in its own present moment, even though we see it as it was 2.5 million years ago. Stars are being born in its spiral arms at this very moment in the galaxy's reference frame. Massive stars are exploding as supernovae, seeding the interstellar medium with heavy elements. The supermassive black hole at the center occasionally flares as it swallows gas or an unlucky star. Satellite galaxies are being torn apart by tidal forces, their stars joining Andromeda's halo. Gas is flowing, dust is forming, cosmic rays are accelerating through magnetic fields. All of this is happening now in Andromeda's present, a present we won't witness for millions of years. When you look up at the night sky and find that faint fuzzy patch in the constellation Andromeda, remember what you're actually seeing. You're seeing the combined light of 1 trillion suns. You're seeing photons that have traveled for 2.5 million years through the void of intergalactic space to reach your eyes. You're seeing a structure larger than anything else in our local universe. You're seeing our cosmic neighbor, a galaxy bound to us by gravity across the vast darkness of space. You're also seeing a reflection of ourselves. Andromeda and the Milky Way are similar galaxies born from similar conditions in the early universe, evolved through similar processes over billions of years. What we learn about Andromeda tells us about our own galaxy and, by extension, about how galaxies throughout the universe work. We're all made of the same matter, governed by the same physics, sharing a common cosmic heritage stretching back to the Big Bang 13.8 billion years ago. Andromeda is out there right now in its own present moment, even though we see it as it was 2.5 million years ago. Stars are being born in its spiral arms at this very moment in the galaxy's reference frame. Massive stars are exploding as supernovae, seeding the interstellar medium with heavy elements. The supermassive black hole at the center occasionally flares as it swallows gas or an unlucky star. Satellite galaxies are being torn apart by tidal forces, their stars joining Andromeda's halo. Gas is flowing, dust is forming, cosmic rays are accelerating through magnetic fields. All of this is happening now in Andromeda's present, a present we won't witness for millions of years. When you look up at the night sky and find that faint fuzzy patch in the constellation Andromeda, remember what you're actually seeing. You're seeing the combined light of 1 trillion suns. You're seeing photons that have traveled for 2.5 million years through the void of intergalactic space to reach your eyes. You're seeing a structure larger than anything else in our local universe. You're seeing our cosmic neighbor, a galaxy bound to us by gravity across the vast darkness of space. You're also seeing a reflection of ourselves. Andromeda and the Milky Way are similar galaxies, born from similar conditions in the early universe, evolved through similar processes over billions of years. What we learn about Andromeda tells us about our own galaxy, and by extension, about how galaxies throughout the universe work. We're all made of the same matter, governed by the same physics, sharing a common cosmic heritage stretching back to the Big Bang 13.8 billion years ago. The fact that we can understand Andromeda at all is remarkable. We evolved on a small planet, our brains shaped by the need to find food, avoid predators, and navigate social relationships. Nothing in our evolutionary history prepared us for comprehending structures millions of light years across, containing trillions of stars. Yet here we are, able to measure Andromeda's distance, map its structure, determine its composition, and predict its future. That's a testament to human curiosity, to our drive to understand the universe we inhabit. Thank you for joining me on this journey across millions of light years and billions of years. If you found this exploration meaningful, please consider liking and subscribing to the channel. Your support helps me continue making these deep dives into space and our place within it. Until next time, keep looking up at the night sky. Keep wondering about what's out there beyond the darkness between the stars. Keep marveling at the fact that we, small as we are and brief as our lives may be, can understand something as vast and distant and ancient as the Andromeda Galaxy. The universe is incomprehensibly large, filled with trillions of galaxies, each containing billions or trillions of stars. Yet here we are, on a small rocky planet, orbiting an average star in an ordinary galaxy, and we can comprehend it all. We can measure it, map it, understand its history, and predict its future. That's the real wonder. Not just that Andromeda exists, but that we can know it exists and can understand what it is and what it means. Sleep well tonight, knowing you share this cosmos with something as magnificent as the Andromeda Galaxy. And remember, every time you see that faint smudge in the sky, you're looking at 1 trillion suns shining across the incomprehensible void of space, a monument to the universe's scale and creativity and the long, slow dance of gravity and gas and stars across billions of years. Good night.